into the realm of exponential functions. So first we just had to be able to compute with exponents. So you see on the left some of the properties of the exponents, and I want to kind of emphasize the relationships here. That in the first one, when you multiply two terms with the same base, you add their exponents. And when you divide two terms with the same base, you subtract their exponents. This third one I always call the power to a power. So when you raise something like a to the m to the power of n, you end up multiplying the exponents together. And the last one it handles are square roots, that when you have a fractional exponent, it's the root of the variable, the root of the base that you want. So what we can do is we can maybe pause our video and just practice a few of these real quick. I'll come back to you in a moment. All right, so let's see what we got. So over here I'm going to use my multiplication rule, and I'm going to get -6, 3 times -2. And now I'm going to have my common bases of x. I'll put like x to the first up there. So I get x to the 5th and then y to the 5th as well. Multiplying the bases, you add the exponents. Now we'll do a little bit of division. And I almost like to think of it this way because I want to write it with positive exponents. So first I'll reduce 15 over 10, and that's 3 over 2. I like to think of it this way. There's one x on top and there's two x's on the bottom. So after they cancel, there's one x on the bottom. And likewise, 4 y's on top, 1 y on the bottom. So there's 3 y's left, and they're on top. So if you want to just write it as 3y cubed over 2x, that would be cool. Now be careful here, because I know that a lot of people want to do like multiplying the bases, the power to a power. So they're going to get a y to the 12th. I'll work from the right back to the left, and then x to the 8th. But don't forget, you need to also do 3 to the 4th. You might want to think of this as like 3 to the 1st power to remind you to multiply 3 to the 4th power. So then that's going to equal 81 x to the 8th, y to the 12th. And our final one, the denominator tells us the root to take. The numerator tells us the power of that root. So I'm going to be doing the cube root of 8x to the 6th to the 4th power. So let's work inside. The cube root of 8 is 2. The cube root of x to the 6th is x squared. Because remember, x to the 6th is like x cubed times x cubed. So that's where we get the cube root of that to be x squared. Raise that to the 4th. So now we're going to get 16x to the 8th. Two others that you want to think about. Anything to the 0 power is 1. And anything with a negative exponent is the reciprocal of the function. So now, take a minute and see if you can simplify this one. All right, so one thing that I like to do is I'm going to put my negative exponents on the other part of the fraction and make them positive exponents. So I'm going to rewrite this as 4x cubed squared. I'm going to take this negative exponent, bring it to the top, and make it positive. And that's a 3, we'll make it ugly, times 2x squared. And on the bottom, we're going to bring our 3x to the negative 2nd in the numerator and make that positive. And notice this last term here, 3xy to the power of 0. That's just 1. So let's see, where does this leave us? This leaves us at 16x to the 6th times 2x squared. And on bottom, I'm going to get 3x to the 2nd power, which is 9x squared. So if I simplify this a little bit, let's see, 16 times 2 is 32. Maybe the best I can do is 32 over 9, and it looks like my x squareds cancel, so I have an x to the 6th in my numerator. So we can leave it like that. That's about the best we can do with it there. So that's a good little review from all the stuff you did in Algebra 1, maybe Algebra 2 as well. This leads us into the idea about solving an equation where the exponent is the variable. So these exponential functions that we're going to solve are one-to-one functions. So as long as the bases are equal, the exponents are equal. So in this first one, my bases are 5, so I just have to solve 3x minus 2 equals 10. Add 2 divided by 3, x is equal to 4. Cool. This one's a little bit different. So I got to think, can I write 27 as 3 to the something power? Sure can. So I can get my bases the same because 27 is 3 to the third power. And now I get x plus 2 equals 3, so x equals 1. Now, in this one here, it's a little bit different because I don't know like 4 to what power equals 8. I don't really know that. But what I do know instead is that I can express both of them with a base of 2. 4 is 2 to the second, and I'm going to multiply by that exponent. And 8 is 2 to the third. So my bases are the same, so my exponents are equal to each other. 2x plus 1 equals 3 times x plus 2. And as we solve that, we do some distributing. We're going to get 4x plus 2 equals 3x plus 6. And that's going to give us x equals 4 as our answer. So you should be able to solve some equations right now. Let's take a look at an exponential function. And we'll use y equals 2 to the x, or f of x equals 2 to the x. So first, a couple questions about it. You see the table on the left. The graph is in the middle. What would the domain of this function be? What would the range be? Try the limits. What do you think they are? I'll wait for you, don't worry. All right, welcome back. So it looks like you can have any input you want for the domain. So the domain is going to be all real numbers. But when you start looking at the values of the range and you look at the graph, it looks like as our x's decrease each time, or our y values are dividing by 2 in this case, so they'll always stay positive, they'll never equal 0. So the range then is y is greater than 0. So when you take your limit then as x approaches negative infinity, as x goes this way, our graph gets closer and closer and closer to that x-axis, but never reaches it. So the limit of this is 0. It never reaches it, but that's the limit it approaches. But on the other side, as x goes off to infinity, this graph just keeps getting bigger and bigger and bigger. So that limit goes off to infinity. I want to go back now to this idea of the range and the limit as x approaches negative infinity. That's going to lead me to the fact that I have an asymptote, a horizontal asymptote. And that's going to be at the equation y equals 0. So for that line y equals 0, that's the horizontal asymptote of the graph. That's when our graph is approaching as x gets really, really, really small. All right, so now if you know what the graph is like, and if you understand your transformations, you can tell me how each of these graphs are formed from the graph of y equals 2 to the x. Again, pause the video and then come back. Welcome back. Okay, well, like before, this plus 3 means it's a vertical shift. You're going to be moving that graph up 3. That's what the number on the end does. It adds it up or moves it down. Now, if we add 3 to the x value, though, that's our horizontal shift. And what you might remember is that the horizontal shift goes in the opposite direction of the sign. So x plus 3 is really x subtract negative 3, which means we're moving this graph to the left 3. And a 3 multiplied by the function is going to be that vertical stretch of 3, where each y value is 3 times higher. And if we multiply the x value, the input, by 3, that's our horizontal stretch, or horizontal compression, if you will. So horizontal compression of 3. If we look here in this bottom middle one, we're really taking the function y equals 2 to the x and negating it, so that flips it over the x-axis. That's our reflection over the x-axis. And if we negate the input, that's where we reflect over the y-axis. So please notice that the ideas behind these transformations stay the same, but the function keeps changing. You have a lot of experience with this, with rational functions, with polynomial functions, with quadratic functions. It happens for exponentials too. All right, this is one of my favorite things. Have you ever heard of the natural base? The natural base is e, and it's a limit. It's the limit as x approaches infinity of this expression here. Now, I've got something for you. Let's see if I can bring it up. All right, so here's a table of values. I'm going to kind of walk you through this table of values. So first of all, I'm going to change x by a factor of 10. And I plug in 1 into this expression here. You can see in my little formula bar what it's doing. It's taking 1 and then adding it to 1 over this column here, and then raising its sum to that power. So if I increase this and go here, notice how it increases. Now this is 1 plus 1/10 to the 10th power. This is 1 plus 100 to the 100th power. Now I'm just going to drag this down, and we're going to see what happens as x goes off to infinity. Notice it's increasing, but it starts to increase at a decreasing rate, and it kind of starts to slow down a little bit. So we say that this value e is about the value like 2.718. That's a good approximation for it. It is a button on your calculator. So I would expect if you do some calculations with it, you'd use the calculator's button, and you wouldn't necessarily use the, what's it called, the approximation. All righty. And where are exponential equations used? Well, like everywhere. You ever make yourself a cup of coffee or a cup of hot chocolate or a cup of tea? It could possibly be modeled by this equation here. So if you want to pause the video for a minute or two, work through a couple of these questions, let's talk about it. All right, so first, let's find what t of 0 is. So t of 0 is when we plug in 0 for t, so we get 70 plus 90 times e to the negative 0.1 times 0. Well, when we multiply by 0, we get 0. So this becomes e to the 0 power, really, which is 1. So e to the 0 is 1, so we get 70 plus 90, which is 160. So what do you think that means? Let's interpret it now. What does that represent? Well, that might be the initial temperature. So maybe when we first made that coffee and stuck a thermometer in it, it was 160 degrees. Yikes. Well, likewise, let's find the temperature after 5 minutes. If we want to find t at 5, we'll just plug in negative 0.1 times 5. And if you go to your calculator and type all this in, you should get that this is about equal to like 124.5877 and a bunch of other numbers. So the temperature then, let's say it's about 125 degrees if we round it to the nearest degree. Pretty cool. Now think about the limit here for a minute. As we take this limit as the value of t goes off to infinity, let's just look at what the equation's doing. So first of all, as x gets bigger and bigger and bigger, the value of negative 0.1 times t, what's that thing doing? It's actually approaching negative infinity. And then let's think about what happens to e to the negative infinity. This is what happens as x gets really, 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 really small in an exponential function. So e to the negative infinity is approaching 0. So now I get 70 plus basically 90 times 0, which is 70. So what does this mean now in terms of the context of the question? Well, what it means is that as you let that cup of coffee sit on your counter, the temperature is going to approach 70 degrees. What do you think is special about 70 degrees in this question? Maybe it's the temperature of the surrounding area. You're in a room that's about 70 degrees. You might know from physics or from chemistry that if you leave a hot or a cold object in a room, over time it's going to approach the temperature of that room. It's going to be approaching the temperature of its environment. Now, you might be thinking, okay, that's pretty cool. I can plug in numbers and get the temperature. What if I want to know, for example, when the temperature is 100 degrees so I don't burn my mouth? Okay, so now you're solving for the exponent. We're going to get to that in a little bit. We'll have some fun with that soon, believe me. So maybe use your graphing calculator. Give it a shot if you haven't done so already. Graph it. See if you can solve this graphically. Alrighty, I went to my handy dandy Desmos and I graphed it. Check it out. The red graph is my exponential function. And if you look at it, the initial temperature looks like it's around 160. And it looks like it's leveling off right around, what is that? That's 100, that's 50. So is this like 70? That kind of all makes sense what we were talking about before. But at 100, it's the point 10.986. So if we round that to the nearest minute, I'm thinking maybe it's like 11 minutes. So if we leave our cup of coffee for 11 minutes and then take a sip, we'll be pleasantly surprised at the nice temperature to warm up our bodies but not burn our mouth.